So what will you do if you have a combined case? And what I mean with that is, what if the far field stress is not the one we analyzed? So what I mean with that is we already analyzed this case here. We analyzed the case of a plate with an axial stress that's far field. But what if I have a stress state that has more than one direction? So now I have a stress state that's basically I have this far field stress, I have this far field stress. How do I deal with those cases? Or I have a stress field that's pointing downwards against the plate, and then this sigma naught is pointing outwards. How do I deal with that? So you can use superposition actually to solve some of these biaxial load cases. And you can use the sigma theta theta equation in a smart way. And you can look at the variations of that in many ways to be able to solve the problem. So for example, for me to arrive to this case, say, let's consider this case first. I can break up that problem into problem number one and then problem number two. Now I know the stress state here and I know the stress state here. So I know the stress state there, point A. I know the stress state here in point B for case one. For case two, I know the stress state here C. I know the stress state there D. So let's examine a point A. In point A, I expect that the stress state in point A is going to be 3. We already said that if the loading direction is this way, then the highest stress should be the hoop stress, and that stress will be 3 times sigma naught. And then I have the case on the right, and then I also said that at point B, it will be minus sigma naught. We already covered that. At point C here, though, the load is applied upwards like that, right? In that direction. So you can actually do the same thing. At point D is 3 sigma naught. At point C is going to be minus sigma naught. So I can superimpose both of those. And what you find then is that at point A and C, when you add them up, you get 2 sigma naught. So the stress at the hole is 2 sigma naught. And then at point B and D, you also get 2 sigma naught. And so that matches what we got for the plate under, this matches what we got here, which is 2 times T for that case. We showed it here, 2 times T. Doesn't matter where you are at the hole. It turns out that using the area stress formulation, I'm also able to get the same answer, that you get 2 sigma naught regardless of where you are at the hole. I hope that was clear. So then, since that's clear, well, then we move to the case where I'm applying compression to the plate in the y direction, but I'm applying tension to the plate in the x direction. You can see here the sign, the arrows. In the x direction is in tension, in the y direction is compression. So that actually causes higher stresses. And so you wonder why that is. So I think it's worth it then to do it step by step. So point A, we already discussed what happens at point A, but I'll do it again just so that it kind of, it kind of sticks. So if I'm applying a sigma naught at point A, I should expect a 3 times sigma naught, the hoop stress. And at point B, I expect it to be minus sigma naught, as discussed earlier. Now, this one is going in compression now, which is not something we had seen before. And so how you use the equations? Well, you don't have to worry. Do what we've said before, which is to note that what you can do is put in here the negative sign of sigma naught. At this point here, you can put R equals A. And when you do all that, what you find is that this point C now, let's put this point C now, point C, you'll find that that's going to be the plus sigma naught. And you're going to find that this point here will be the minus 3 sigma naught for point D, say. So now I'm ready to see what the total effect is. The hoop stress is the highest here at this point and at this point. And that's 3 sigma naught. So 3 sigma naught plus sigma naught is 4 sigma naught. So that's the stress state right there, 4 sigma naught. And the stress state in this right here is going to be different. That's going to be minus sigma naught plus let's see if I got this right. Minus 3 sigma naught, that's giving me minus 4 sigma naught. I probably have an error there. But I invite you to check it at home. All you have to do is superimpose the stress field for each of these cases. And if you do, then you can get the answers that you're looking for. But I think it's correct. So stress state for this case is quite a bit. There's other cases you can do. You can apply just a pure state of shear stress. And if you do look at this case, rather than looking at this case, you can get fancy and you can look at the case of, hey, you know, I would like to find a solution for a plate on the shear. What do I do now? Because everything I solved was for this one. Well, we can use the idea of max principal stresses. If you recall, we can use a plane stress transformation equations that we had where you had tractions applied like this, shear stresses applied this way. What I can do is convert the problem using max principal stresses. And if I do that case, then all you have to do then is, right, because this here using transformation equations is equivalent to this case right here at a 45-degree angle. So all you have to do then is decompose this one into two cases. Analyze this first and then analyze this next. So get the stress field for this one, get the stress field for this one, add them up, and then you get the total effect of what happens at the hole. I did it here so you can see it. So say that's the far field stress. Well, you know, that's 3 times, this point here is going to be 3 times the far field stress. This point here is going to be positive 1 times the far field stress. We already discussed that. And this minus 3 times tau. So when you add the effects, you get this here. So actually, this case we already analyzed. This case is this exact same case I had discussed where I got 4. I got 4 there. And I got minus, remember we got minus 4 sigma naught there. That's exactly what I'm getting now for the shear case. You can see there, 400 minus 400. I mean, it's 4 times, but all that's saying is that it's 4 times. It's just done in percentages here. The more general cases, if I were to have stress fields applied far field, and I have shear stresses applied far field, if I have this information, I can tell you what the stress state is going to be at the hole, and the equation is here at the bottom. So this is the general formula you can use for any case, which is very powerful. Because say you have a fuselage you're analyzing, and I don't want to model any of the holes of the fuselage, they're circular holes, say. If I know the stress states there, I'll plug it into here, here, here. I'll use the finite code. Instead of modeling the hole, I get the far field stress, apply it to each of these formulas, and now I can calculate the effects at the hole. So rather than modeling the hole, you can take advantage of these solutions in a very, very simple way without having to worry about it. So yeah, so anyway, so that's very cool. We in summary, we cover stress concentrations where the stresses drop as you go away from the hole. I'm showing it here. None of the formulas here you have to memorize. because these are just fundamental equations that you can find in textbooks. So, but you need to understand the theory, what's happening. And I think I was quite clear about what's going on. You have a hole that disturbs the far field stresses in the body of the material, and then you have to figure out where the structure is going to fail, and that's near the hole. And we need to figure out when it's going to fail, and we know that value is 3 times the stress concentration, 3 times the stress, remote stress is the stress concentration at the hole, the magnitude of that. So we learned that you have that stress concentration factor that occurs. Experimentally, people have used photoelasticity to prove that that is the case. So that's a colorful fringe pattern that people have used to indicate the intensity of the stress for a lot of these structures. And so, just to point out, photoelasticity is an experimental method that allows you to it allows you to use optical properties of the material to understand the mechanical deformation, and allows you to determine experimentally the stress distribution in the material, which is a very powerful method that really allows you to do a lot of things. And so in these experiments, optical refractive devices are used, and those refractive devices allow you to show you a fringe pattern. And the closer the fringe patterns are, is where the highest stresses could be. And so the very, very useful, powerful method that has been used historically. And then that's another example of the photoelasticity being used. These methods have been very successful at showing what the stress fields are and match very well the area stress function calculations we showed. Here, what I show is 3 things. Let me go step by step so you understand what these are. So here, the analysis is not an infinite plate now under axial load. Now this is a plate that has finite width. And what I'm showing here is in part A, a loaded plate. In part B, I'm showing a photoelastic model, basically the experiment that was conducted. In C, I'm showing a stress distribution, okay? And so what I want to show is from photoelasticity, they did a cut here, and they could show that the stress at a particular cut was 320 psi. And if you do a cut in zone B over here, you get that. And by the way, we're looking at a point here, point A, but that's the zone I'm talking about. Zone B is this one here, and we're talking about that point here over here. That's 280 psi. But the maximum value from photoelasticity was found to be over here at this point near the hole, much higher, 1130. And you can see it's quite high. It's not actually 3 times 320. You can see here, 1130, which is the stress concentration at the hole, is not 3 times 320 because that's going to be equal to 960. The reason in this case you're not getting a factor of 3 is because now you have finite width. And finite width is going to change what the formula looks like. It's going to change what it is. And people came up with formulas, like here you can see the formula here for the stress concentration of the hole. So if you have finite width, now if you have infinite width, meaning D was infinite, you can see that this goes away because D infinity means that these terms go away. You can quickly see that KT becomes 3, which is exactly what we had before. So people have come up with formulas for finite width equations that allow people to be able to calculate what the effects of the stress concentration are. And in this case, what they did, they calculated the stress concentration a little bit differently. So they didn't do it relatively to the 320, because from 320 to 1130 is more than 3, obviously. What they did is a little bit different. That's why you need to learn these formulas and how they're used in real life. What they did, they calculated the sigma nominal first. What does sigma nominal mean? Well, I have a far field stress of 320, but what is the stress right here? What is the average stress right here in this section here, right? Well, you know what that is because say you have a load applied P and the thickness was T, then the cross-section area is T, and then if you take D minus 2R, D is the width of that plate, which is this distance here, and 2R is the width of the hole. What you're doing then is you're getting the average area, you're getting the area across that plate, and obviously without the hole. So that's the formula you see here, and that's the sigma nominal. So the KT you're calculating here goes multiplied to the sigma nominal to get you the maximum stress at the hole at point C. Point C is over here. It turns out that when you do the calculations and you plug in 2.31 over here to KT, you can see this KT 2.31 is very close to the experiment of 2.35. But in essence, you can calculate the max stress using this equation. So 2.31, that's the way you will do it, 2.31 times the load applied P divided by T, D minus 2R. And when you do the calculation, you arrive to the 1130 you see there. It's going to be very close to 1130. So that's how you do it when you have a finite width. You're going to use the formulas I provided to you. I'll give you a list of formulas towards the end so you can understand how to use them. And so in real life, given a application, what you will do is you, depending upon, because every book is different, right? Every book will provide you a different formula you could use. In this case, they're doing it relative to the sigma nominal, and that sigma nominal is the stress over here. Again, sigma nominal is a stress going across here by the hole. So not the sigma naught, the far field stress, but the stress going across that plate with the hole there. So again, what is the stress there? Stress equals load divided by area. The area there is the thickness of the plate, D minus 2R. That's what sigma nominal is. And that's what this is it. And so in this particular book, because every book is different, it tells you how to apply it. It tells you to calculate the maximum stress, you have to use this formula. It's telling you, okay, calculate sigma nominal first, do that calculation first, and then calculate KT using this formula. Well, you know the width of the plate D, you know R, which is the radius of the circle, plug that in to get KT, which is 2.31, and then from that information, you can quickly plug it in here, 2.31 times sigma nominal. And sigma nominal can be calculated using this formula. And so it should be fairly straightforward calculation. With that, I'll stop here and move to the next lecture.